Hello, in this video, we present the design of synchronous sequential logic using D-flip. There is a procedure for the design, consists of the following steps, but before that, we would like to make sure that it's clear what the design mean. Usually, we have set of specifications, problem description, and design means that we need to determine the logic diagram or circuit diagram that meets these specifications. The procedure consists of 7 steps as below. First and most important, from the problem description and the specifications of the desired operation, we derive a state diagram for the circuit. I believe this is the most important step. Then we reduce number of states if possible, and we assign binary values to the states, obtain the binary coded state table, and then determine or choose the type of flip-flop, derive the simplified flip-flop input equations and output equations, and finally, we draw the logic diagram of the circuit. Example. The example that we take is to design a circuit that detects 3 or more consecutive ones in a string of bits coming through an input line. This is all what we are given. And from these few words, we are required to design a digital circuit that meets these specifications. Let us first explain what do we mean by the problem. We want to design this circuit here, which we denote as a black box, and this has one input, which is called X, that represent a string of bits, in addition, of course, to the clock, because all these circuits are clock sequential circuits. There will be one output only, and this output will be 1 if there is 3 or more consecutive ones, and the output will be 0 otherwise. Let us describe more what do we mean. Suppose the string X consists of the following: 1 0 1 0 1 1 0 1 1 1 1 0 1, etc. So that is X. The output Y should be 0 0 0 0 0 0 0 0 0 and 1 here, because we have 3 ones already occurred in the input, and also we have 1 here because the problem says 3 or more ones, and then 0 0, etc. So let us start our procedure. We said the first step is to find the state diagram for what we call the sequence detector. And the state diagram here, we start as follows. We assume we are in an initial state that is called S0, and its output is 0. S0 is initial state, which means we will start looking at the sequence. And it means that we have no ones yet, or we can say that we have 0 ones so far. If we receive a 0 while we are in S0, we remain in S0 because we have no more ones, no ones received. However, if we receive 1, we must go to a different state that we call S1. Its output is 0, and S1 means that we have 1 already received. And then from S1, if X becomes 0, we go back to S0, and if X is 1, we go to another new state that we call S2. S2 means we have 2 ones received already. And then when we are in S2, if X is 0, again we will go back to S0 to start counting from the beginning. And if X is 1, we go to the new state that we call S3. The output is 1, and this means that we have 3 consecutive ones that appear, which are this one, the first one, and this is the second one, and this is the third one that brings us to S3. Now, while we are in S3, as long as we receive 1, we stay in S3 because the problem says 3 or more ones. So more ones, we can get 4th and 5th and 6th, we stay in S3. And the first 0 that comes when we are in S3, we will go back to S0. So this is the state diagram that we develop. And as we mentioned, this is the state diagram we should reduce number of states if possible. It is not applicable here because it cannot be reduced further. And then we assign binary values to the states. This is arbitrary, of course. We have 4 states here, and therefore we need 2 flip-flops, and these will take the values 0 0 0 1 1 0 1 1, we can arbitrarily assign 0, 0 to S0, 0, 1 to S1, 1, 0 to S2, and 1, 1 to S3, or any other assignment you see fit, it would work. There's no problem. Step number 4, we obtain the binary coded state table. This will be obtained from the previous state diagram. By looking at the diagram, we find if we were in state 0, 0, and we can go back to the diagram to look at it if needed. If the input is 0, we stay in 0, 0. And the input is 1, we go to S1, which is 0, 1. And the output was 0 in both cases. When we are in S1, which is 0, 1, if the input is 0, we go back to 0, 0. If input is 1, we go to S2, and output is 0 in both cases. And if we are in S2, if the input is 0, we go back to S0 again, which is 0, 0. And if the input is 1, we go to S3, which is 1, 1. And the input is 0 in both cases while we are in S2. Now coming to S3, which is 1, 1, the output will be 0. Sorry, the output will be 1 under all inputs. If we receive x is equal to 0, we go back to 0, 0, which we defined initial state. And if the input is 1, we stay in 1, 1 in the same state as long as the input is equal to 1. And this is the binary coded state table that we use in the next step to define the inputs of the flip-flops. Now, we know from before the flip-flop input equations and output equations for the D flip-flop, which are, as if we can recall from the past, a Q at time t plus 1 is equal to D at time t. Here we have two flip-flops. A at time t plus 1 is equal to D of A, and B at time t plus 1 is equal to D of B. Therefore, from the next state that we have just derived as a function of the present state and the input, we can find out A of t plus 1 and B of t plus 1 by looking at this table here, and we can draw a kernel map to A of t plus 1 and another kernel map to B of t plus 1. A of t plus 1 equals 1 for the combinations 3 and 5 and 7. So we can put this here on this kernel map. This is 1 here, and this is 1 here, and this is 1, which is a 3 and 5 and 7. And therefore, we have two loops on the kernel map. This loop here and this loop here. And we can say that A of t plus 1, which is equal to D of A, will be equal to AX plus BX. Same thing, we do it also for B of t plus 1, which is 1 for the combinations 1 and 5 and 7. Therefore, on the kernel map, we have three min terms. This one here, which is 1 and 5 and 7. And we have two loops on the kernel map. This loop here and this loop here. And therefore, D of B equals AX plus BX prime. Finally, the output Y can also be put on the kernel map, which is 1 for the two combinations 6 and 7. Therefore, we have 1 here for 6, 1 here for 7, and we say that Y is equal to A and B. Actually, with this, we are almost done because we have the equations for D of A and D of B, and we have the equation for the output. From the binary coded state table and the kernel maps, we have obtained A at time t plus 1 as a function of A at time t, B at time t, and the input x, and also same thing for B at time t plus 1 as a function of A, B, and x. Therefore, D of A, which is input of flip-flop A, equals AX plus BX, and D of B equals AX plus B prime X, and Y equals A and B. Actually, with this, the diagram is so easy to draw now, because all we have to do is to draw two flip-flops first, which are this one, D of A, that's input D, and the second one is B, which has output B here, and this is input D, and each one will have its own clock pulse connected together. Now, D of A, as we found here, equals AX plus BX. Therefore, all we need is an OR gate to make this ORing here, and then we need two AND gates, one to produce AX, so this comes from A, as we can see, and this is X, this is AX, and this one comes from B, and this is X, this is BX. Therefore, this is input D of the first flip-flop. Same thing exactly for D of B, it's equal to AX plus B prime X. Therefore, AX, which we derived here, same output of this gate will be input to this OR gate here, and the second one is ANDing of B prime. This is B, and this is B prime here. We write B prime and X. So this is B prime X, and this would be D of B. The output Y is so simple because it's A and B. And this completes the synthesis of the sequential circuit using the flip-flops.